thermal fluid sciences experts. This is ProReady Engineer.
Hello, this is Bassam Abdelnabi from ProReady Engineer. I'm excited to share a new video series featuring industry cases. If you like what you see, please consider liking and subscribing. Take care and talk to you soon.
Today, we're diving into a fascinating case study in high-stakes aerospace engineering. We're going to break down how a really complex liquid fuel pumping system was designed not just for raw performance, but for something even more critical: emergency readiness. And honestly, that's the perfect way to frame this. This whole project wasn't about patching up something that was broken. The client needed to innovate to create a brand new capability that would seriously expand their combustion testing flexibility, pushing the boundaries of what was even possible in their lab. Okay, so let's get into the nuts and bolts of the challenge. They had to engineer a system that could handle two very different modes. First, a standard dry liquid fuel, and second, a precisely controlled water emulsified fuel for really advanced emissions testing. That dual mode requirement right there adds a huge layer of complexity. And the performance demands? They were just extreme. I mean, we're talking about pressures over 3,000 pounds per square inch. To give you some perspective, that's more than 100 times the pressure in your car tire. It's a massive engineering hurdle to clear. On top of that incredible pressure, the system also had to deliver a flow rate of 1,500 pounds of fuel an hour. It's that combination of super high pressure and super high flow where the engineering gets really interesting and, of course, really challenging. You know, hitting performance numbers is one thing, but when you're in an environment with this much pressure and flammable material, the single most critical question you have to ask is about safety. What happens if there's an emergency shutdown? How do you protect not just the people, but hardware that's worth hundreds of thousands of dollars? And that's exactly where the ProReady engineering philosophy comes into play. It's a whole approach that looks way beyond just the target numbers on a spec sheet. It considers the entire operational life of the system, especially what happens when things go wrong. So the heart of this philosophy is a concept they call failure envelopes. What that means is you don't just design for when everything is running perfectly. You actively plan for and engineer solutions for when things are a little off, and most importantly, for flat-out emergencies. It's all about building safety in right from the very beginning. So how did this philosophy actually translate into real hardware? Well, the solution was this incredibly robust, integrated system built around a three-stage architecture. Each stage serves a very distinct and very critical function. So first up, you've got the high-pressure pumping skid. That's kind of the heart of the whole operation. Then there's the water and emulsion control stage, which gives it all that operational flexibility. And third, the integrated purge system. Think of this as the guardian that ensures everything stays safe during a shutdown.
All right, let's look at that first stage. This is the foundation, the hardware that's responsible for generating that massive 3,000 plus PSI of pressure. But, raw power is totally useless if you don't have intelligent safety controls to back it up.
And this is what's so brilliant, the layered defense. There isn't just one safety mechanism. There are three of them, all working in parallel. You've got a burst disc for a catastrophic overpressure event, a mechanical relief valve for more controlled situations, and an e-stop link solenoid that instantly vents all the pressure on command. That redundancy is absolutely the key to making a system intrinsically safe. Now, the second stage is what gives the system its really unique capability. A dedicated water pumping loop was integrated to mix with the fuel, creating this perfectly stable emulsion. This is what allows the client to do that sophisticated emissions control testing, something that was just impossible for them before. And that brings us to what is, you could argue, the most critical safety feature in the entire design. This is the system that protects the hardware when a test has to be shut down right in the middle of a full power run. So the danger here is something called fuel coking. When a test stops suddenly, there's still fuel left in those super hot lines. That fuel can basically cook, turning into a hard carbon gunk that can clog up and completely destroy expensive downstream parts in just a few minutes. It's a huge risk. So the solution is just plain smart. A simple system might just blast a fixed amount of nitrogen through to clear the lines. But this system, it uses a pressure-referenced regulator. It's actually tracking the operating pressure in real time and injects the perfect amount of nitrogen needed, whether the system shuts down from idle or from full power. This is how you prevent an incomplete purge or even dangerous flame spikes. Of course, a great design is just a theory until you prove it works. So the system went through some incredibly rigorous validation and commissioning tests to make sure every single component and safety feature performed exactly as it was engineered to.
In this table just brilliantly illustrates the success. You can see the validated results for every key metric. Seamless switching between the fuel modes, full range flow control with absolute precision, and most importantly, they verified instant depressurization and a perfect purge response during simulated emergency tests. It just worked.
So, what's the bottom line? The project delivered on its initial promise. Big time. This wasn't just a piece of hardware they delivered. It was a whole new capability. The client could now perform a way wider range of tests and do it more safely and more reliably than they ever could before.
So what's the big takeaway from all of this? Well, it really comes down to a standard of engineering that goes so much further than just meeting the numbers on a piece of paper.
This quote just captures the entire spirit of the project perfectly. The goal wasn't to just build a pump that could hit 3,000 psi. The real goal was to deliver a complete, reliable, and safe capability that would serve the client for years and years to come.
At the end of the day, the system delivered on 3 core promises. It was technically precise, hitting every single performance target. It was operationally flexible, opening the door to new kinds of testing, and it was intrinsically safe, engineered from the ground up to handle the absolute toughest conditions and unexpected events.
And that really sums it all up, doesn't it? True reliability isn't just about performance. It's something you build by engineering for both peak performance and for emergency readiness, making sure that a system is rock solid, no matter what state it's in.